Hello guys, welcome on Tesla Eduventures. In this video today, we are going to discuss the pressure formula exerted by an ideal gas on the walls of the container. So you can see that this is an imaginary container, cubical container, obviously, and its side is A by A by A. And there are many molecules of a gas filled inside this container, but I am just talking about any one molecule. So we know that this any one molecule will be having a velocity v1, which would be v1x I cap as well as v1y j cap plus v1z k cap. This would be the velocity of this molecule, and let us suppose that its velocity in the x direction is vx instead of v1x. Now we know that this molecule will go and strike on this wall, and the collision will be perfectly inelastic, and then it will return back with the velocity vx because collision is elastic in fact. So in elastic collision, you know that the momentum and the velocity just changes its direction with the wall, and this ball will return back with the same velocity vx. Now let us start our time that at t is equal to 0, this ball started to move in this direction going away from this wall, and it would take a time of a by vx to move till this wall. Then it will strike this wall and it will again rebound with the same velocity vx, and it would again strike this wall after a total time of 2a by vx, because it would take a time of a by vx to go in forward direction, and then it would take a time of a by vx to come back to the original wall. So if we wish to find out the change in momentum first of all, so we know that at the time t is equal to 0, the momentum was mvx in this direction, and at this time the momentum is mvx in this direction. So the change in momentum will be 2mvx, and the time taken will be 2a by vx, and therefore the average force applied by this particle on this wall will be equal to change in momentum upon time taken, and change in momentum is 2mvx upon time taken is 2a by vx. So the average force applied by this particle per unit, in fact average momentum transferred per unit time, that is force, is mvx square by a, where a is the side of the container. Now we know that for n molecules, if we assume that all the molecules are moving with the same speed, we are just assuming that. In real case, it is not the scenario. In reality, all the molecules have different variety of velocities, and that distribution is being plotted by Maxwell. We would have a separate video on that topic. So the total average force will be equal to nmvx square upon a. Now you can see that obviously this is the total average force, and if we talk about the fact that the net speed of any one molecule will be under root of vx square plus vy square plus vz square, and this vx, vy, vz are the random speeds in all three directions. Therefore the probability that the molecule will move with the same speed in all three directions is high. Therefore we can say that vx will be equal to vy will be equal to vz, and hence we can say that v will be equal to root 3 times of vx, and from this we can say that vx is equal to v by root 3. So Vx is equal to V by root 3. Now we have already written the force. Force was Nm Vx square upon A. So F is Nm Vx square is V square by 3A. Now we obviously know that all the molecules are having different speed. So the first molecule will be having a speed of V1, that is equal to under root of Vx1 square plus Vx2 square plus Vx3, in fact Vy2 square plus Vz2 square. And similarly for n number of molecules, the speed can be written. But we know that all the molecules have different velocities, different speeds, V1, V2, V3. So we cannot assume that all the molecules have same speed V. So what we should do, that we should take an average of V square, and average of V square will be V1 square plus V2 square plus V3 square up to Vn square upon n. So we would be taking this value instead of V. So F would be equal to Nm V square average divided by this 3A. Now you can see that this V square average can be written as V RMS if we put a square root on this. So V RMS will be equal to V1 square plus V2 square up to Vn square upon n. Now you can see that what is root mean square velocity. The sequence of spelling this velocity is root mean and then square, but we calculate this velocity in the reverse sequence. We first of all square up all the velocities, then we find out the mean of their square. So mean can be calculated by adding those velocities and dividing by the number of molecules, and then we put a root over them. So that is root mean square velocity. So what we can write this velocity as V RMS, and we can square this up. So we can also write this V square average as V RMS. So this is V RMS. Okay. And now if we wish to find out the pressure, so pressure is equal to force per unit area, F by area, and area of this container, wall area of this container is A square. So pressure of this container, pressure of the gas on the walls of the container is Nm V RMS square upon 3A cube. And A cube is obviously the volume, so pressure is equal to Nm V RMS square upon 3 into V. Now this N into M is the total mass of the gas, so we can say that pressure is equal to mV RMS square by 3V. Now we know that if P is equal to mV RMS square by 3V and mV RMS square by 2 is average kinetic energy of the molecules, and this is obviously translational kinetic energy. This is translational kinetic energy because we are taking the velocities Vx, Vy, Vz. So this is the translational kinetic energy. So we can say that mV RMS square is equal to twice of average kinetic energy, which is translational, and we can substitute this value over there in the place of mV RMS square. So it is 2 by 3 kinetic energy average per unit volume. So if we denote this with U, which is kinetic energy density, so we can say that the pressure acting on the walls of the container due to gas is 2 by 3 of kinetic energy density. Okay, and obviously we know that PV is equal to nRT, and PV is equal to N, which is mass of gas upon molecular mass of gas. M naught will be the molecular mass of the gas. Let us write down M naught as molecular, or we can say molar mass of the gas. Molar mass of gas. So this is RT, and P is equal to M by V into RT by M naught. Okay, so we can write down P as this. So M by V is the density, and this is RT by M naught, and this is 2 by 3. Kinetic energy per unit volume will be half rho V RMS square. What we have done, we have written the kinetic energy as half mv square V RMS square, and mass upon volume is written as density. So cancelling this 2 with 2 and this rho with rho, we can see that V RMS is under root of 3 RT by M naught. Okay, you have already heard this formula. So this is V RMS, and if we write down M naught as M into Avogadro number, where M is the mass of one molecule, and Avogadro number you know, then we can write down that let us use the next page. Yeah, so V RMS will be equal to under root of 3 RT by M naught can be written as M into Avogadro number, and R by Na is Boltzmann constant. So V RMS is equal to under root 3 KT by M, where K is Boltzmann constant, and value of K is 1.38 into 10 raised to power minus 23 joule per Kelvin, and M is the mass of one molecule of the gas. So this is M. So this was the complete information about the relation between the average kinetic energy per unit volume of a gas, ideal gas, with the pressure of the ideal gas. And in the next videos, we'll be discussing some more important concepts of kinetic theory of gases. Thank you.